This is a video report for Lab 2, Motion of a Falling Object. In this lab, I dropped an aluminum can, which is my system, and deduced from its motion the outside forces acting on my system, which were the drag force and gravity. I then created two computational models that simulated the object falling, one with just gravity involved and the other involving gravity and the drag force. Even though the results were visible, had we used a system with a larger surface area, the results would have been more dramatic and easier to see. Moving on, I used Tracker to obtain the time and position data. I set up the up direction as the positive Y, and I set to the right as the positive X direction. I then used a measuring tape that I held to set the calibration stick to 1.5 meters. Alright, let's go ahead and run this thing. After running this, we produced our position by time graph, which gives us our data points over here, our X and our Y. Using the skeletal code provided for VPython, I produced a computational model that only focuses on gravity and is based on the principles of Newton's second law. Here we'll put the object to start at roughly the origin, and it will start with a velocity of 0 because it starts from rest. Moving down, we write our equation for the weight force, which equals F net, and it also equals the negative mass of our object times the force of gravity times j hat, which gives us our direction. In this particular model, this equation for the weight force equals the F net force because we're not taking into account any of the other forces that are acting on our object. Moving on, we can see that we use our equations from Newton's second law. Final velocity equals initial velocity plus F net divided by mass of the object times delta t, as well as our position equation, where the final position equals initial position plus the velocity of our object times delta t. Let's go ahead and run this model and see what we get. Here we can see our object being simulated as falling, and then over here we get our predicted plot points. Comparing our position by time graph from our experimental data with our position by time graph from our model, we can see that they're very similar. However, there's a small difference down on the lower right side that suggests that there's a separate external force, which is the drag force, acting on our system. Now let's look at a computational model that includes the drag force. Scrolling down, we can see our proportionality constant, which is used in our equation to find the drag force. The drag force is characterized by the equation drag force equals the proportionality constant times the magnitude of the object's velocity squared times. And because this model takes into account both drag and gravity, the F net equals the weight force plus the drag force. Let's go ahead and run this so we can see our visual of this model. Okay. Here to the left, we can see our object falling, and down here on the right is our position by time graph. Let's see a graph with both of our models and our experimental data on it. Looking at our prediction with the drag compared to prediction without the drag, it is more accurate in predicting our experimental data. As stated in the introduction, the data does not differ greatly because the surface area of our object does not allow for much drag. So what does all of this mean? In order to understand this, we need to go back and take a look at our previous computational models. This is a graph of our velocity times time rather than position times time to compare our prediction without drag and our prediction with drag. We also need to understand the concept of terminal velocity. Terminal velocity is when the drag force is equal to the weight force, causing a constant velocity, so the object will only continue at that velocity and no faster than that velocity, which is deemed the terminal velocity. Understanding what terminal velocity is, we can go on to make the statement that terminal velocity can only be found with the drag force, because after all, it is when the drag force equals the weight force. So comparing our two models, we see that the prediction with drag is the one that can predict the terminal velocity, whereas the prediction without the drag cannot. As we see here, the prediction with drag, the orange line, becomes more straight as the time progresses, suggesting it becomes a constant velocity, whereas the yellow line, the prediction without drag, stays curved and appears to continue in an upward fashion. What if our object was thrown downward instead of starting from rest? We can see from a computational model that even though the object is thrown starting at a greater velocity, the terminal velocity would stay the same because it is independent from the initial velocity.